Okay, so today we're going to look at transformations on functions. And so I'm going to show you my set of notes that I have for this, and I want to point out a couple things. So first off, in my notation that we see here, the letter C represents the constant, just any kind of number. P of X represents the parent function. And so if we look at this, I want you to see this transformations in a couple of different ways. First off, we'll see that there's two sections here. There's a top section where I show you the transformations in there and how to read them based off of function notation. And then down below is I gave you a parent function of x squared and showed you the transformation form or standard form of a quadratic. And then we're going to look at how each of the letters and where they are in your equation and how they relate to the transformations also. Since we're mostly going to be using this technique, it's important to see how these are laid out. Secondly, I want to look at transformations in two types. Transformations that affect the graph in a vertical sense, that's up and down, and then transformations that affect it in a horizontal sense, right and left. And so let's look at these. We'll look at them up here in the function part. And here is a translations, or if I have a function and then I add or subtract a number, a constant, after the parent function, then that is how the graph moves up and down. If I have a negative out in front of the parent function, then that would be a reflection on the x-axis. So it basically takes it and flips it up and down over the x-axis. And then if there's a number out in front, that's going to represent a vertical stretch and shrink. And we'll talk about that in just a moment. For the horizontal, you'll notice that all the transformation parts take place inside the parentheses with the x. So if I have a minus c or plus c inside, that's right or left. If there x is negative inside the parentheses, then that would be a reflection on the y-axis. That would be a side-to-side action, kind of like reflecting on the y-axis like a door, back and forth. And then we have horizontal stretches and shrinks. If there is a number, it'd be multiplied inside. So if I have transformations inside, like this one is illustrated, the B and the C, those would represent horizontal transformations, and the A and the D represent vertical transformations. So why? Why does that happen? Let's take a look. I'm going to take my go-to parent function of x squared, and let's look at the up and down. So for vertical, if I have a function f of x, and I have x squared plus 1, then I can see that I have a constant on the outside, and so that falls into the translations up and down. Since I'm adding a constant outside, then I would go up that many units. So this would be representing up 1 unit. And likewise for the other one, what if I have the reflection would look like this, negative x squared, where the negative is in front of the parent function. And we can even look at a stretch. In this case, I have a number multiplied to the parent function. These are vertical things because they happen outside. And what this means is that vertical transformations change the y value. And what I mean by that is this. If I take a number and I plug it in for x in a parent function, let's say 3, for example, if I plug in 3, then I will square the 3 and I get 9. All the vertical transformations make you plug in the same thing again. So let's plug in 3 into this one. The first thing I do here is I have to plug the 3 in, then I square it, and I get that 9 again. And then I change the answer by adding 1. Same thing here. If I plug in 3, the first thing I have to do is square the 3, get in the 9, and then the negative changes the 9 to a negative. And likewise here. I do the 3 squared first, get the 9, and then times it by 2. So that's why they change only the y values, because I have to get the y value first. That's how vertical transformations are dealt with. So this one moves the graphs up and down. This one will reflect it over the x-axis. So the normal parent function, real quick sketch, looks something like this, coming down here and touching the origin and going back up. This one would be moved up 1 unit. This one, because it's a reflection on the x-axis, would be upside down, just like that. The parent function flipped over the x-axis. And then a vertical stretch and shrinks, when that number is bigger than 1, then you are doing a vertical stretch or expand. And if it's less than 1, like a fraction like 1/2, then it would be a shrink or a compress. And so we just say that this right here is a vertical stretch by a factor of 2, or a vertical stretch by 2, meaning I'm taking this parent graph, and if I grab the bottom and the top, and I just pull it apart, they'll get tall and skinny. So this graph, in comparison, would look a little bit taller and skinnier than the original. And if it was a fraction, like 1/2, this would be a vertical shrink. And that's like taking it and compressing it or pushing backwards into each other, which makes the graph go low and wide. It's a little bit wider than the original. So vertical shrink, vertical stretch, reflection on the x-axis, up and down. In this case, it was an up. If it was down, it would be moved down. And so remember that vertical transformations change the y value. What about horizontal? What's going on there? This one causes a little bit more confusion for some people, and because it seems backwards than what would normally happen. So if I think in here I have x minus a number, then that means I'm going to move to the right that many units. If I have x plus a number, then I'm moving to the left, which is kind of like the opposite of what we would think. So just like vertical transformations change the y values, what's going on here, and we'll just do another example, use the same one. F of x is, this time I have x plus 1 squared. So what's happening here? Well, let's take our same example of 3. And what's happening here is, if I plug in 3, I'm not squaring 3 first. What I have to do first is I have to add a 1 to that. So the number that I'm actually squaring is the number past 3. And so these affect the x's. So horizontal transformations change the x value. And it kind of is like saying, yeah, well, if I plug in a 3, I'm going to get a 4, and I'm squaring 4. But what it's saying here is at 3, I'm going to get the answer that I would have gotten at 4. Okay? So what it's doing is it's doing a whole shift backwards. So the answer for 4 got shifted backwards to 3. Okay? That's why that is a left transformation. Sometimes that's difficult for people to remember that. Plus, it gets a little bit more intense. So what happens here is this graph is going to move back 1 unit back this way, like so. Now, a way that can help you, and we're going to use this equation part down here, because this is how it's going to pretty much manifest in our things, our equations. Okay? So one way to help you deal with that is, let's take that. And let's just do one that has 2 things. Let me put it this way. Let's take this quantity right here that's in the parentheses. So anytime you see this in the parentheses stuff, there's 2 things that can come in here. We got to have a horizontal stretch or shrink, or we're going to have a right or left, or both, or even a negative. Okay? If you see the negative in front of the x, then you already know that you have a y reflection across the y-axis. So if I take this, and I think this process right here, what do I have to do to get this back to, say, x? Or what do I have to do to this thing to make it 0? So in other words, in our parent function, it's x. There's no number with it in the parentheses here, and so there that would just be a 0. So how do I get back to that? Well, I have a +1 here. To get back to it, I have to subtract the 1. And so then I get x is -1. And when I solve for x in this scenario, I'm going to get this number. Okay, and that number actually coincides and represents this scenario. If that is a -1, then that means -1 in relation is to the left. It's negative, it's to the left. And so I can say that I'm moving to the left 1 unit. This is what I'm illustrating down here. Okay. What if I had more numbers in there? What if I had 2x minus 1 squared? So what would be the transformations associated with this? Well, I know because I'm subtracting a number that I'm going to have it left and right. I know because there's a number in front that I'm going to have a horizontal stretch or shrink. And by the way, stretches or shrinks horizontally is like an accordion. If I'm stretching it, I'm going to pull it longer and wider. Kind of does the same thing as that. And if I have a shrink, I'm going to compress it in this way, kind of like that. So they're kind of like the opposite of these things. So again, those two things are going to be manifest from this, but we want to make sure we get the right numbers. Many people make an error in thinking that I'm going to be moving this thing according to this pattern right here, that I move it to the right 1 unit. And that is not the case because that number here messed it up. This is why I tell people how do I get back to the x? Now, I'm not interested so much in, we're not solving an equation to solve it. The solve is going to tell me the right or left number. Okay, this is your right or left. But I'm interested in also this number in the front because this is how the understanding of the stretches and shrinks occur. If I solve this, I have to add the 1. So I have that. But the next part here is the important part. So the next part determines if it's a stretch or a shrink. Why is this over here going to be a shrink when there's a 2 sitting here? Intuitively, a 2 here was a stretch. Makes sense. But a 2 here is not a stretch, it's a shrink. Why? Because again, the question, how do I get back to the x? How do I undo that times 2? Well, I have to divide. But instead of thinking divide, think multiplication. And you just flip that number over. If I multiply both sides by 1/2, I have the x equals again. And we'll need this right here. This 1/2 is my right or left. This is positive, it's going to the right. But this act right here of multiplying by 1/2, that's the number that determines the stretch or shrink. Because that's a 1/2, 1/2 means it's less than 1, so it would have to be a shrink. And that's why when you look at these notes right here, and you look down here, you'll see there's that reciprocal action right there. This is where it comes from. It comes from this part right here. What I had to do to get rid of that number, just take the reciprocal of it, and that determines if it's going to be a stretch or shrink. If it's bigger than, if that number, that's how you read it, that number right there, which is R number 2, if that number is bigger than 1, then I will have a horizontal shrink by 1/2. And if that number is less than 1, then I'm going to have a horizontal stretch by, and then you take the reciprocal of it that way. So one way to look at these things, and you can write the note for this if you want, is solve this for 0 to find the right or left. Take this number right here and flip it over to determine a stretch or shrink. Flip the B over, and that will determine the stretch or shrink. And so that's the idea of the horizontal information. So again, whatever that number is, so if I have another function right here, and I write in here 1/3 x plus 2, then what do I know? Well, first off, I know I'm going to have a right or left, so I need to solve this for 0. So we subtract the 2, and we'll get 1/3 x equals -2. And then I have to flip that over, and so x is -6. So I'm going to the left 6. Left 6. That's how you would write your answer for that. The negative means to the left 6. But do I have a stretch or shrink? Well, if I take the reciprocal of that, I'm going to get a 3. And 3 is bigger than 1, so that implies that I'm going to have a stretch. So I will have a horizontal stretch by 3. And that's how you would describe that one. This is a horizontal shrink by 1/2. And you're moving it to the right 1/2 units. That's how you would write those out. And so that's what you see down here at the bottom of this. When you look at it, I just go through all this with you. The right or left is determined by taking C divided by B, C divided by B, which is what we were doing when we solved for 0. Okay? So that is what's happening for those. Let's take a look at some other examples and see what we can come up with. Here is an example that you might have to end up doing on similar to your homework. And I think this is number 19. I'll give this to you. So f of x is x minus 2 to the third, and g of x is a negative x plus 2 to the third. And so what transformations have to occur to go from this one to that one? And so one technique, there's many techniques you can do here. There is no one way. I'm just showing you how you can use a graphical representation to help you out. The parent function for these two happens to be x to the third. Because we did our parent function graphs, we know what this looks like. And so it's nice to know that. That's why you want to know your parent functions. And I can draw a quick sketch of what the parent function looks like. It looks something like that. This is p of x. And then by transformations, I can graph these other ones. From this one right here, I can see clearly that this is going to be 2 units to the right. So I can come over here and just kind of like mark off and then draw this thing over here. The same picture. And this right here is f of x. This is at 2. But this one does what? It has 2 transformations in it. The one on the inside, so let's say right or left. And this means I'm going to go, if I solve for x, I'm going to get -2. I'm going to go to the left 2. And that tells me that I have a reflection on the x-axis, which means I'm going to flip it over. So I'm going to take the parent function. I'm going to go to the left to -2. Normally it would look like this. But because I flip it over the x-axis, it goes in the exact opposite direction. So it'll do something like this. Like this, come off like that, and go like that. It's not a very good picture, but it serves my purpose. So this is g of x. So if I draw a picture of both of them, then I can try and describe the transformations associated with what's going on here. To get to g from f, I have to do what? I have to move 4 units to the left. So move 4 units left. And I have to reflect it over the x-axis. And so you write reflect over the x-axis. And that's how you would do that problem right there. Again, you don't necessarily have to draw the picture, but it does help. Now, a couple other things too you might be asked to do. And I'll just give you this little note right here. If I draw a picture of something, and let's just say I put this over here, it's going to be at -5, and I draw a graph like so. And I ask you, what would be the equation of this? What's the equation of this graph? Well, the first thing you want to do is identify the parent function. Well, this looks like a square root graph. And a square root graph starts at 0, 0 and goes off in that same direction like so. This is P of X. So what is this one? What is this F of X going to be? You got to write me an equation for that. Well, you want to look to see what's going on. Start with the right, left, up and downs, and reflections. Those are pretty straightforward. So we can see we're going to have to move this point back to here. That's back 5 to the left 5. So then I can use my knowledge of transformations for that. There's no reflections going on because it's going in the exact same direction. But the main one here for equations, and then what I want to write down for equations, from graphs. If you have a stretch or shrink, so if a stretch or shrink occurs, assume that it is a vertical stretch or shrink. And then always, if possible. So it's very difficult to identify a horizontal stretch or shrink from a picture that you're trying to get. It's just easier to look at it as a vertical stretch or shrink and try and find that number that doesn't, because they are related in some fashion. So that would be my hint to you for looking at drawing graphs, equations from graphs. Another one I want to look at real quick is how you can do something like this. This is in function notation. So I have this function right here. This is f of x. All I know about f of x is it's got these little line segments, and I have these points, negative 2, 4, 0, 0, 2, 2, 4, 0. And what I need you to do is identify, here's y. It's in function notation this time. And I need to graph this y and identify the transformations from f. What's going on? So we want to list these transformations. What's happening? I'll show you how we can go about doing that. We can let's look at our transformation page and see that all the things that are associated with it. So I see that I have inside the parentheses, I have an x minus 1. So I know I'm going to move to the right 1 unit. I have a 2 out in front over here that it corresponds with this concept. So that would be a vertical stretch by 2. And then I have a plus 2 over here, which means also that would be an up 2 units. That's how those work. So the list of the transformations, you start from the inside and work your way out. I'm going to go to the right 1 unit. I have a vertical stretch by 2. And lastly over here I'm going up 2 units. So some people wonder, well, how do I graph this? What am I supposed to do? Well, remember, in a transformation, every single point follows these transformations. So all you have to do is just take these 4 points and do these transformations. And then you can connect the dots again, and that's how you would graph this. So let's start with this one right here. Actually, let's start with this one. So I'm going to go to the right 1. If I go to the right 1, I'll be here. Then I need to stretch by 2. Well, remember, stretches, vertical stuff changes the y value. The y value here is a 0. So timesing by 0, 2 by 0 is still 0. And then I just move up 2 units. So this point goes here. So this point is that point transformed. Let's do this point. Go to the right 1. Now the y value here is a 2, and I'm going to times it by 2. So that is going to become a 4. So now I'm here. And then I need to go up 2 at that point. So now I'm up here at 6. The 0, 0, go to the right 1. The y value is 0, so times 2 would be 0. And then go up 2. And now I'm here. It makes sense since these 2 dots are on the same line. These 2 dots should be on the same line. And then we have one more dot to do. Move to the right 1. I'm at negative 4. When I times that by 2, that gives me -8. So now I'm here. And then go up 2 puts me at -6. And then we just take our ruler and we connect these dots in the same fashion as they were connected in the original. And what you're going to see when I get done is I'm going to see this same kind of shape, but stretched and shifted over. So it's a little bit taller and skinnier, and it's shifted over 1 unit. And then you can mark the new points on this graph right here. So this would be -1, -6. This over here would be 1, 2, 3, 6. And this one is 5, 2. And this is your Y graph. And so that's how I can transform a picture that's written in function notation form, identifying the transformations and redrawing the new shape. And so that is transformations. If you have any questions, make sure you ask me during class time.